Hey growers, welcome back to the castle for another episode of Science for Growers. You know I normally like to do my videos outside, but it's a little too cold today. So the fire's on, come on upstairs and we'll talk some science. As we're coming up the stairs, this is our guardian knight, Sir Robert de Burgh, who died in the 1300s. This is a tomb rubbing that was done probably about 125 years ago by a woman that worked for the British Museum. So he's our guardian knight, Sir Robert de Burgh. Okay, here we are inside the castle. It's definitely a little warmer and a little more comfortable. The last video that I did was on calculating PPM levels when you're using dry nutrients. And one of the big questions where some of you had asked was, who cares? Why does it make a difference? So we talked a lot about, we know from a lot of scientific data now, we know what plants need, whatever plants you're growing. We need the nutrient levels in the precise balances and ratios at different plant growth stages. If you have too much of a nutrient, you're wasting money and you're apt to cause toxicity problems, which will translate into quality, yield, and money loss. Too little of a nutrient means you're at suboptimal growth, and again, it's going to translate into poor quality, poor yield, and a loss of money. So we talked a lot about the need for balance and for a comprehensive fertilizer, one that has all of the necessary nutrients in exactly the right ratios to each other and at exactly the correct PPM levels. So you need to know what you're giving your plants. Because these calculations are based on the metric system, let's do just a real quick review. Remember, 1 liter of water at room temperature weighs 1 kilogram. 1 kilogram is 1,000 grams. 1 gram is 1,000 milligrams. So 1 kilogram is 1,000 times 1,000, or 1 million milligrams. That's where we get this term PPM, or parts per million. If you put 1 milligram of a nutrient salt into a liter of water, you have 1 milligram put into 1 million milligrams, so you have 1 part per million. So with that quick review, let's move on now to the nuts and bolts of how do you make these calculations work in your grow operation. We've already looked at dry nutrients. In this video, we're going to look at liquid nutrients. Okay, what I've done is set up just a few examples of some of the liquid nutrients that you might see at any store that you go to. They can be different brands. This is a Fox Farm. I don't know whose that is. Now the Fox Farm, Neptune's Harvest, all good fertilizers. And just like we saw with dry fertilizers, whenever you look at a fertilizer, you're going to see numbers on the front of it, 3 numbers. This one's a 644. The Neptune's is a 264. This one is a 10-10-10. As we saw with dry nutrients, those 3 numbers refer to your 3 macronutrients. The first number is nitrogen. The second number is phosphorus. The third number is potassium. And what the number indicates is what percentage of that product is represented by that particular nutrient. So in something like a 10-10-10, the first 10 is nitrogen. It means that 10% of that product is in the form of nitrogen. So let's just take an example, a random example, and use a fertilizer number that's, let's say 10-6-4. When we're looking at liquid nutrients. What does this mean to us in terms of our ultimate goal of knowing what the ppm level we're delivering to that plant? So if we're using our example of a 10-6-4, 10% of that product is nitrogen. And if we go back to the review we just did, we want to remember that 1 liter equals 1 million milligrams. So 10% of this product is in the form of nitrogen. So what we have to do when we think of this calculation is first think of having a liter of this product. Because whether we have a cup or a quart or a pint or a liter or a gallon, the concentration is going to stay the same, but we need some reference point to know what that concentration is. So we're going to take a liter. So we know in a liter we have 1 million milligrams. 10% of that is going to be in the form of nitrogen. 10% of 1 million is 100,000. So this product with a 10% nitrogen, the ppm level of that is 10% of 1 million. This is actually in a concentration of 100,000 parts per million undiluted, this 10-6-4 product that we're looking at as an example. So that means that if we just gave our plant a shot of this fertilizer undiluted, we will be giving nitrogen at the level of 100,000 parts per million. What we want to be giving our plant, on average in a vegetative state, is somewhere around 200 to 250 parts per million. So you can see, obviously, we do not want to be giving this concentrated, but we have to be very precise in how we get that 100,000 parts per million down to 200 to 250 parts per million. So let's look at how we do that. First off, we have to look at this process of dilution. If I take 1 part of this product at 100,000 parts per million, if I take a tablespoon or a cup or a liter or a quart and mix it with the same amount of water, we're diluting that by a factor of, we're cutting that concentration in half. So let's follow that train of thought. We use liter again as a standard for how we make these calculations. So we take 1 liter of water. This is a 2-liter container. So we take 1 liter of water and let's, for example, add 1 tablespoon of this 10-6-4 product, which has a nitrogen concentration of 100,000 parts per million. If we take 1 tablespoon, we have to know how much we're diluting that when we put it into a liter of water. So if we look at a liter of water, 1 tablespoon equals 14.786 milliliters. So if a liter is 1,000 milliliters and a tablespoon is 14.786, let's say 14.8 milliliters, if we divide 1,000 by 14.8, that means that we have 67.6 or 68 tablespoons per liter of water. So if we take and put 1 liter of water into a container, and then we take our product, which at its unconcentrated level is 100,000 parts per million. We take a tablespoon of this and put it into 1 liter of water, which is 68 liters. We've now diluted this by a factor of 68. So it's no longer at 100,000 parts per million. It's at 100,000 divided by 68. So it's at about 1,470 parts per million now when we've put 1 tablespoon into 1 liter of water. But we generally don't deal in liters when we make up our nutrient feed tanks. We talk in terms of gallons. So all we have to know is that 1 gallon equals 3.78 liters. So we've already taken 1 tablespoon of our product, put it into here, diluted it down from 100,000 parts per million to 1,470 parts per million. A gallon is 3.78 liters. So if we take this liter that we made up, or we take that 1 tablespoon of product and put it into a gallon of water, we have diluted it by another 3.78 times. So we take that 1,470 parts per million in the liter and divide that by 3.78, and now what we come out with is a PPM level of 388 parts per million when we take that 1 tablespoon of the 100,000 and we ultimately put it into a gallon. We used the liter first because that's how we do our calculations, but ultimately we can take that 1 tablespoon of 100,000 parts per million nitrogen, put it into a gallon of water, and we have now 1 gallon with a nitrogen ppm concentration of 388. Why do you have to be so careful when you do your measurements? Because if we use something that we think is a tablespoon, but it's a teaspoon, which a lot of people make the mistake of doing when they're measuring, there's 3 teaspoons in a tablespoon, so now we have to take that 388 and divide that by 3 because we're doing another dilution factor, and we only have 129 parts per million per gallon if we add a teaspoon. This is why you have to be precise. We know what our plants need. Whether you're growing lettuce or high value plants, the data is there, and if we're giving 129 parts per million when the plant would like 250, we're going to have suboptimal growth. It's going to cost you quality, it's going to cost you yield, and it's going to cost you money. So precision, precision, precision. Let's take this calculation just a little further to show you how to do one more critical calculation. So now let's even fine-tune this a little more. We gave you an example of, let's just randomly take a tablespoon of product and show you how the dilution calculations work. But now, you as growers, we look at our chart and our science data, and we know that we want to deliver, let's take an example, we want to deliver 250 parts per million to our plant, and we're going to use this same product. What we have to do is kind of reverse the math. We know we want to reach 250 parts per million. So what we do first is we take that 250 parts per million that we want to reach, and we multiply it this time by 3.78 to find out what the concentration would be in that liter we're using as our standard to do the calculations. We're just reversing what we did the last time. So we take the 250 or whatever number, 200, 195, that you want to reach, multiply it by 3.78 to find out what concentration we have to be in a liter to finish our calculation. So if we take the 250 and multiply it by 3.78, we come up with a number of 945 parts per million per liter. That means when we do the first dilution down, we need to be at 945 parts per million. The 945, if we look back at our last calculation, was taking that 100,000 parts per million concentration of nitrogen in our product, dividing it by the dilution factor we used before. We used a tablespoon because it was 68 tablespoons. Now what we're trying to figure out is what that dilution factor is. So we now have a 945 parts per million concentration in the liter. We know that the product started off is in its concentrated form is 100,000 parts per million. We want that dilution factor. So in simple math, all we do is 945 equals that 100,000 parts per million in the product divided by that unknown dilution factor. Just simple algebraics gives us 9. We multiply each side by x to clear the division of x on the right side of the equation. We equal 945x equals 100,000, which means that x equals 100,000 divided by 945, which equals 105.8. That's the dilution factor. Remember in the last example of 1 tablespoon, the dilution factor was 68 because there were 68 tablespoons in that in a liter. The dilution factor now is 105 times dilution of the original product. So if we know that there's 1,000 milliliters in a liter, and that's what we're working on, all we have to do is take that 1,000 divided by the dilution factor, which is that 105.8, and we come out with 9.45 milliliters. That's what we have to add to either the liter, because that's what we did our calculations. Then we put the liter into a gallon jug and put the rest of the water in on top of that. So it means we take 9.54 milliliters. And remember that there's 14 milliliters in a 14 and some change milliliters in a tablespoon. So we're at a little more than a half of a tablespoon. That's why very often with products you want to be using an accurate measuring device. If you're in American standards, you're going to be using teaspoon, tablespoon, or if we're dealing with a lot of these products, because we're dealing with liquids that are calculated on liters, you want to use an accurate shot glass milliliter measuring device. So that's all there is to it. I know some of you are probably sitting there and saying, what? Go back over it a couple of times. It's just very simple math. Once you see it, it's like riding a bike or walking a tightrope. Once you do it a couple of times, it's like, oh, I get it. Is it a little work? Sure. Will it get really easy for you after a couple of times? Yes. Is it that important? And I repeat that. Is it that important? Undoubtedly a big yes. The agricultural world, and especially the high-value world, is all driven now by return on investment, cost of production per unit of product. It's that important. Too little nutrient delivered to your plants, suboptimal growth. It's costing you money, quality, and yield. Too much, and we can go into this whole world of induced deficiencies, which we talked about in my last video, and I would suggest that you go back and look at that last video so you get a review of some of the things we're talking about and the importance of things like checking the ECs going in, checking outflow ECs, having your water tested, and knowing how to do these calculations, and understanding that the numbers on the front of the bottle are a guideline for you to be a precision grower. Too many growers they'll look and say, oh, the third number's highest, that must be a better nutrient. You have to know what you're giving your plants. You have to know exactly how much they need, how much that product's going to deliver, and how to do the dilution of liquid products so that you're delivering that final PPM level that we know your plants need. I looked around for a calculator to help you in your process. I found this little one from an orchid grower in Russia that I've included the link to. The numbers that I've run through, they've come out well every time I've run them through. So take a look at it and get used to using it, but take the time to learn how to do these ppm calculations, both with dry nutrients and with liquid nutrients. So until next time, remember to be good to each other, and remember, you need to know what your plants need to grow.